one lecture first on some impact of foam-filled tubes. Okay. Then after that, this is not very long. Okay. This is a little shorter lecture. Most of the lecture is actually 1 hour. This will be maybe 35 minutes, 40 minutes. So what I will do is I'm not going to continue. I'm not going to take a break and continue with the second. Okay. And then we'll take a break. Is that okay? But if you want to get up and go out, feel free to do that. Okay. But what I'll do is I'll continue. And as I said before, feel free to ask questions. Okay. You don't have to wait till the end of the lecture. Alright, so let us start then. So this is the title, is Reinforced Polymer Forms Response to Dynamic Rolling. So what I'm going to do here is today, now what you already have kind of known by now, since we have talked so much about foams, that these are open cell or closed cell. They can be flexible or rigid. So this is something extra that I'm adding now, that it is either flexible or rigid. Till now we were basically talking of metal foams, so this flexibility aspect was not there. Now we are talking about polymer foams. Okay. So polymer foams, they are used in insulation, as you know, and actually the bed you sleep on, most of them, that's also a polymer foam. Okay. And packaging, it's used a lot. You use bubble wrap or you use foam type of material around it. Sandwich panels, energy absorption, we already talked since, just like in metal foams. Sometimes they use your filtering, okay, some water filtering or something like that. Non-slip surfaces, so especially if you go to, if you are climbing on a slope or like a ramp, so they might put some thin sheet on there, and that is generally of some sort of foam. So when you step on it, some air goes out and you get a little bit of suction and your foot kind of sticks to it. So so what I will talk about is polyurethane foam, both flexible and rigid. Okay. And that foam will also be reinforced with fibers. Okay. So we have all these combinations. Why polyurethane foam? Because it's one of the most versatile polymers and it is used a lot. Okay. And it's very durable and hence contributes to long lifetime of products. So what that means is that it can last a long time, it doesn't degrade. For example, if you take polycarbonate, that's also a polymer, but when it's subjected to UV light, what happens to it? So even all these lights we have in the room, they are giving out some ultraviolet portion in the light spectrum. Or if it is in the window, then from the sun you are getting ultraviolet light also. So over a period of time, like maybe a few years, that foam, polycarbonate starts to become yellow in color and it starts to have small cracking in it, and that's called crazing. So it begins to degrade. Whereas these are much more durable, they can last for a long time. Okay, and hence you don't need to keep making it after every few years. And that's where this long lifetime of products comes in. This is, we already talked about, these are the different applications where polyurethane foam is used. Now, the beauty of this also is that you can process it into a thermoplastic or a thermoset. Okay? So you can make both. And as you can imagine, the thermoplastic will be the flexible foam and the thermoset will be the rigid foam. So how you make foam here is that you have a urethane group, okay, and so basically it's a reaction between some sort of alcohol and an isocyanate. So you will buy this foam in two parts, okay. And so one will be the urethane and the other will be the isocyanate, and when you mix them together, then there is a reaction and there's some gases given off and it begins to foam. Okay. So now so you have this polyol component and isocyanate component. So this polyol, which is this part here, and then the isocyanate, which is this part, you can then also tinker with that by adding certain chemicals to it to slow down the reaction or make it fast or slow or whatever, however you want to do it. And the other thing is that if you have low molecular weight, then the foam becomes rigid. If the chain lengths are smaller and the molecular weight is smaller, then the foam becomes rigid. If they are long chains, then it becomes flexible. Okay? Because long chains by nature, it's just like if you have a very long rope, it's much more difficult to keep it straight. Okay? And a little bit of wind or whatever, any vibrations will make it move around. A small chain or a rope, you can keep it straight. Okay? You can keep it straight and rigid. So, well, I kind of jumped here a little, so that's what is being said here. Okay. So how did we make this? So what we did was, these are the ingredients used. 22 weight percent of methylene diphenyl isocyanate, that's the isocyanate part, and 78 by weight percent is the polyol part. Okay. And then the reinforcements were this. These are either milled e-glass fibers or chopped glass fiber strands, 6 millimeters long, which means quarter-inch long. Okay. Or we also use hollow glass microspheres. So these were about 0.06 millimeter diameter, but that's the average dia. It varied between about 40 to about 100 microns. Okay. The filler material is first mixed into the polyol, okay, and then MDI is mixed into the fiber reinforcement and the polyol mixture. Chemical reaction starts, it is exothermic and it begins to get warm. So what you do is you mix it, okay, you can, with a mixer, you can have a mechanical mixing system. You mix it nicely and then you will see that its temperature will begin to rise. You can just feel it, or you can have some sort of measurement thermometer or something to measure it, or you can have a thermocouple to measure it. As soon as the temperature begins to rise, you put that mixture, which is just like a thick liquid, you put it into a mold. Okay, so if you want to make a plate or you want to make a cylinder or whatever, so that's your mold. So once you put it in there, it will then start foaming and fill the whole mold. Okay. Now, and so the reaction starts and the foam rises into the mold, and what we were making was a quarter millimeter thick plate. But we were also doing something else. I'll show you that. So now you need a specific type of material for the mold. Otherwise, what's going to happen? This polymer will stick to the mold, and then you'll not be able to take it out. So what do you do? How do you ensure that it doesn't stick to it? Any ideas as to what you can do so it doesn't stick to it? Particular temperature. No, there's no temperature there because once you put it in,
Sir,
it is
some type
clear.
of releasing agent should be applied.
Yeah, okay, that's a good point. So he's saying that you add release agent. So this is your plate mold, so you put release agent on it, that's one way. But what we did was we used Teflon plates. So our mold was made out of Teflon. So Teflon is one material that almost nothing sticks to it. Okay? So you can easily get it out afterwards. So it's a little more expensive, but release agent is also good. You can use that. Okay. And then we used this ASTM test method for compression test and 3-point bed test and drop bed test. We did some of those. And our drop tower was this an MTS drop tower we have, that's the model number there. It has an instrumented drop weight of 76 kg. Okay. And it has accelerometers inside the weight, the drop weight. And you can also put accelerometers on the supports where it falls. Okay, you can put accelerometers on the specimen if you want. So you can do all that. So this is just a 3-point bend test that was being done. Now if you notice here, on the bottom there is something here you see, and that's coming out here right in the center of that tube that we were testing. So that is the LVDT, the linear variable differential transformer, to measure the deflection at the center point as it is being loaded. Okay. Now you will notice this is an aluminum tube and it has foam inside it, and it's a filled aluminum tube. And that's the drop tower. I think Dr. Upadhyay already talked a little bit about it yesterday. So it's almost the exact same concept. So what happens here is that we use this top glass fiber strand reinforcement, and so we saw a few things happen. Okay. The first thing we saw is that reduction in cell size. Let's see if I can enlarge this. So if you see here, then there are all these are long fiber strands here, and then you will have to look, it seems you will have to look at your PowerPoints. Okay, you can access those. It's really hard to see. I was hoping the focus is not that good unless you come right very close to it. So there are all these glass fiber strands, and then so on every side, so this is a glass fiber strand, and then you will see a row of cells right around it, the foam cells. Okay. So they line up right on the surface of the fibers. Okay. And that's exactly how this thing worked out. If you look at, okay, maybe this is a better picture. Okay, so you can see this here. Now this enlarged, so this is the fiber strand, this is a fiber strand, and all these bubbles are lined up, the foam cells are lined up here, and there's another row here. And so they are all kind of bridging the space between the fibers. That's how they end up. Okay, So that's what I'm saying. And then also we found that the fibers are located in the struts of the cells. Okay. And the cells tend to line up as we talk. Cells become irregular in shape with high weight fraction of fibers. So you will see when you add too many fibers, like 70%, 60% fiber weight fraction, then the cells become very disorganized. So that's just another, this is for 25% fiber fraction, and this is how it basically looks. Then we used different weight fractions. We went really high. We went from 25, 75, 90. Okay, that's a really very high. So there's very little polymer in there. So the polymer is basically acting as a binding agent. So all these fibers, and then just the fibers are joined together with very little in terms of polymer. The fibers were coated with silane to improve bonding between the glass fibers and the urethane. So these silane coatings help to create a covalent bond, act as a bridge between the urethane surface and the glass fiber surface. Just by itself, they don't bond as well, but there are certain coatings which are called silanes. If you go, you find any literature, you will find a lot of literature on this. And many companies, they make silanes, and you can buy them without any problem. Then we did these drop weight impact tests again on the same thing. We used aluminum hollow tubes. This is when 0.35 inch thickness, 2 inch diameter. I take this hollow tube and I just pour it from the top, and it begins to foam inside. It takes about 3-4 minutes before it begins to foam. Okay, about 3 minutes. And then it will start rising up. And so I let it rise inside the aluminum tube. See, I cannot do that with the metal foam. See, because in the metal foam, if I take this aluminum tube and I put molten aluminum into it to foam in, what's going to happen? It will melt this tube even maybe. So I cannot do that. So there we have to then cut a cylinder of the foam just about the right size, put it into the tube and use adhesives to bond it to the surface of the tube. In this case, I don't have to do that process. I can just foam it inside the tube. I don't have that temperature problem.
Can you do that for plates?
Sorry?
Can you do this for plates?
Yes, I can take. So if you want to make a sandwich, right? So I take 2 face plates, and that becomes my mold. So all I have to do is I have to put something to close the side. Right? I put it on a base. Let's say it's a Teflon sheet on the bottom. I take two Teflon thin plates. I put it on the side to close the gap on the side, and then just pour it from the top. That liquid, just pour it in and foam and fill it up and become a sandwich with a foam coat.
The cooling that is needed for this, in the cooling during process?
No, there's no need for cooling. It's exothermic, yes, it may heat up, maybe it will become about 45 to 50 degrees C. That's all. That's not much. Yeah, about 50, 60 degrees at the most. So outside, in summer here it's like 40 degrees, 45.
What is the reason for selecting glass fiber?
Reason for?
Selecting glass fiber.
Oh, you can use something else too. We just chose glass fiber because that's the cheapest reinforcement, and it's a good reinforcement. A lot of people always use. Yeah, I know there is a trend towards carbon fibers with this, but it depends. Why would you use carbon fiber? Do you need that
You
fiber?
mentioned at the very beginning that if we use polycarbonate, it is affected with ultraviolet rays, so we cannot go further. So we will go for polyurethane. Likewise, in the reinforcement also we have used glass filled short glass fibers or milled glass fibers. So is there any specific reason to choose only glass?
No. That's the most common which is used, and it's readily available. It's very cheap reinforcement.
But it increases the density.
Yes, it does. Yes, it does. But that was not our criteria. We were not worried about weight at this point. See, if you use this in an automobile, actually this work was funded by Ford Motor Company. So if you put, the weight was not their criteria, because see, so in a car, when you sit in a car, you have the windscreen in front, and then there are these two tubes going like this. Okay, that's called the A-frame. Okay, and then on the bottom, the floor has certain channels in it. So, and then on the back side again, there is on the back seat, on the sides, there are some more channels. That's all you have to fit. So it's not it's very small amounts that you can put in. But the idea is, but they haven't done it yet. They don't, it's kind of, it adds, you see, in an automobile manufacturer, when they are making like, I think Ford makes about 12 million cars a year. Okay. If they have to now start putting this foam and do all that, and let's say it takes, for the front and the back and the floor, let's say it takes another 2 hours. It delays their process by 2 hours. Okay. That means they have to pay all the workers for 2 more hours every day. Right? Plus, if their capacity, they are moving out cars, they may not be able to make 12 million anymore. They might make 11.5 million. So they lost 500,000 cars also. So there is a lot of other things that go into it, okay, which we did not address here. Yes, so suppose by doing this we added, let's say, maybe 2 or 3 kg of weight to the car. Okay, is that going to make a big difference in its fuel consumption? Maybe not. So it's not going to add too much weight.
And on what basis you have selected the minimum length of the fiber? You have chosen 6 mm short glass fibers.
Yeah, so the 6 mm you can buy standard. Okay. 6 mm fibers are available, top strand fibers. See, so whenever, like, when you use bolts, nuts bolts. So if you do your nice calculation, my plate is this thick and that thick, and then you come up with a bolt length which is, let's say, 72 millimeters long. You probably cannot buy 72 millimeters long. It will be custom made. You can probably buy either 50, 60, 70, 80, something like that. Okay. So then you just buy the standard one, which is mass produced. You don't want to go with anything that is custom made unless the economics works out. Okay, so we'll stop this one and then I'm going to go on to the next presentation. We're not going to take a break just yet.
And sir, last one more question.
Yes.
You discussed about the aluminum foams filled with the aluminum tube filled with aluminum metal as well as polymer. Which one is suitable for which application and which is best in which point?
You see, we have not done any tests on filled tubes with aluminum foam. Okay, I've not done those. But with the aluminum foam, you will be able to have higher peak loads compared to this.
Because the metal.
And most likely you will also have higher energy absorption. These polymer foams will not be able to match the aluminum foam in terms of both energy absorption and the peak load.
In regular purpose, we use polymers to reduce the weight.
So it just depends where you are using what. And if you have low intensity load, smaller loads, okay, then you would use aluminum foam. And so, when you have a car crash, you're not talking of, for these tubes I'm doing 300 joules, 77 joules, like that is my impact. There you will have higher impact.
Even most probably these things are used for the structural applications. In structural applications, our motto always to be reduce the weight, increase the energy absorption. How far it can be?
Well, with polymer foams you will actually see the density of the polymer and the aluminum is comparable. They are both about between 2 and 3, and that's for 2.7. So polymers are also between like 2 and 3 grams per cc. So that way they are comparable in terms of weight. But in terms of energy absorption, the aluminum foam is superior. So now this topic I'm going to talk about is really not related directly to dynamic behavior or anything like that, but it's certainly an important topic, and if you want to find papers and work on this, you will find like hundreds and thousands of papers. So this was something as I was talking to Dr. Upadhyay, and he said, well, it's okay, you can add it in there, that's fine. And he wanted to have one more lecture on something. So this is what we chose. So the focus here is on how do you know the property of the interface. So like in this, I'll say, yeah, you add glass fibers, you add carbon fibers, you add this. And you all know that the interface affects the total response or the properties, mechanical properties of the composite. So if the fibers are very weakly bonded, let's say they get even, if you pull it, they will slip out. That weakly bonded. What does that mean then? It is as if that composite has long holes in it, basically. It is that weakly bonded. So no load is transferred to the fibers. If you have it very strongly bonded, then what happens? If they are extremely rigidly bonded, then the material is so brittle that it just doesn't absorb much energy.
Is that interface or interface?
Well, we call it interface, yeah. That's what most people call it.
Interface.
Yeah. So when I am going down to the micro scale, a lot of people call it interface. But you can also still call it interface. Interface, tomorrow's lecture I'll be using interface, FACE. Okay. But what that interface is, I have a composite panel and another composite panel, they are bonded in the middle, so that's an interface. So it's like a macroscopic interface. But when I talk of very small scale like here, then people use this term. So basically then if we want to find that, then there is not many options left for you besides doing this nanomechanical testing. People have been doing pull-out tests and all sorts of things to try to get some idea of the interface properties. But this is something, another channel that we are trying to set. So we know that transfers load from the bulk matrix to reinforcement. So strength of the interface determines the mechanical performance of a composite. So that's why we are trying to do this. So now before you do all this, there are several issues that we need to address. Now this is a very long presentation, okay, so what I did was, when I was making it, I kept putting all sorts of things in there. It has over 100 slides. So I'm going to skip a lot of those in the middle, but they are there, you can spend time later on and look at those. Preparing the fiber reinforced plastic surface for nano indentation. That's the most difficult part. Okay. And we'll address that some more. We want to characterize the glass polyester. We are using now polyester composite. Interface properties for different coupling agents using nano indentation. The coupling agents used are these. The silanes, that's what we're calling. The OTS, this octyl trimethoxy silane. This one, what does it do? It produces a weak bond between the polyester matrix and the glass fiber. So that's called so it creates van der Waals type bonding. This MPS has the pacroloxy, propyl trimethoxy silane, these long names. This produces strong covalent bonds between the fiber and the polymer matrix. Okay. So these are the two, and a lot of your composites people work on, they always keep playing with the interface. So that's why we are trying to do this. Now, nano indentation is generally almost more than 90% of the papers you will find they use this type of a tip. Okay, I'm going to show you that. It's a Berkovich 3-sided pyramidal diamond. Okay, so it has 3 sides like this and one like this. And so what we added to this mix was we did parabolic tungsten tips. Okay, I'll show you that also. So that nobody had done this parabolic tungsten tip. And there are some problems with this Berkovich tip. So I'm going to skip this. This talks about some, the nano indenter, how it works. So that's not really too much of importance to us. So when you start indenting something, so nano indenter means that the tip radius is very small. So it's like 10, 20 nanometer tip radius, very short radius. So when I start indenting here, if I indent only the surface, then I do not get the bulk properties here. Right? So I have to indent through the surface and into the bulk. So it depends. If you only want the coating properties, then you will indent like this. If you want the full properties, then you will indent like this. Now if I add fibers to the mix, now it becomes a composite of some sort. Then if I indent here, then I may be just doing between 2 fibers there is some polymer and I may be just indenting that. See, now we are talking of a 10 nanometer tip radius, so my indent volume may be in the breadth direction, it may be only 50 nanometers. Okay. So I may be just indenting in the polymer, even though I think it is a composite. So you have to be indenting and creating a stress stressed volume which is representative of the composite. Right? Okay. So that's why you need to do that. Now we use polyester because polyester, epoxy, or some other, like polyether and all are the most commonly used composites. So epoxy and polyester are the two most common ones. So we use polyester. And this is just how you cure the polyester. Okay, that's sort of important. Then these composite samples must be polished and etched to obtain a root mean square surface roughness of 10 to 20 nanometers. So that's like very smooth surface. 10 nanometer root mean square roughness. Okay. And it is a multi-phase thing. You have glass fibers which are very hard, and then you have surrounding that is polyester, which is much softer. Glass has what, 70 gigapascal for elastic modulus. What about polyester? About 3 gigapascal. So if you just try to take a polishing table with cloth or add some diamond paste to it, and if you polish it, what's going to happen? You will never get this, okay? Because you abrasively cut some glass fiber, then the stress relief by the glass fiber will be much more than the relief in the polyester, and they will deflect very differently. Okay? So you will end up with a much rough. You will keep polishing, but you will always have a rough surface. So what we have to do is, we have to do a combination of mechanical polishing and chemical etching. Both have to be done at the same time. So that's what we were able to do. Okay. So we did not have any basic theory with us, but we did a lot of trial work and we finally came up with this. We had some basic ideas, but so this is all the chemicals we use. So the first one, this is for coating the fibers with the silane. That's all I already talked about. This ketone peroxide and cobalt octolite, these two are used for curing the polyester. And then this OPS, OPU, OPA solution, 1 micron, 6 micron diamond suspensions, silicon carbide, fine grit polishing paper, all of this polishing cloth. This is, so from here to here is what is used for mechanical and chemical etching of the surface. Now OPS and OPU, these are two suspensions which have colloidal silica particles in it. Those silica particles are 40 nanometers in diameter, okay, or in basic size. And that solution has a pH value of over 7. So that makes it basic. Okay. And it etches the glass. So that pH, that suspension, you can buy this from the market, it etches glass. Okay. OPA's solution has a pH of 3, between 3 and 4. So it is acidic, and that etches the polymer. Okay. So these are the two that were used. Then we first do polishing with 600 grit paper, is very fine polish. Then we did diamond paste 6 micron, then 1 micron, make it more polished, okay, reduce the surface roughness as much as we can. Then we went through this OPS, OPU suspension for 40 minutes of polishing, and then OPA for 25 minutes of polishing. So what this did was, I'm going to skip this is the nano indenture part of it. You can take a look at that. So, or maybe let me go back. See, so the nano indenture, this is what it looks like. So this is just a microscope to look at the sample surface. This one here is the nano indenture, which has that fine, very fine tip. And this is the atomic force microscope. They are all on one head. So they are all moving together. So this can be used to find the surface roughness, the atomic force microscope. But you can also use the nano indenture tip to scan the surface roughness. So we were doing both, but mostly we were using this because this is more accurate than this one. So then I have this here. This is for the OPS solution, and this is the surface roughness. So it was a lot of work. So first we polished it only for about 15 minutes, then 20 minutes, then 25 minutes, then 35 minutes, and so on. Okay, and kept checking the surface roughness. So we found that at this time, the surface roughness came out to be the lowest, and then it started going back up. Similarly with this other solution OPU, we found that at this time we got the lowest and then it went back up. And then this is on the polyester. And this is monolithic, that means just the polyester by itself. There's no reinforcement. And this is how the tip looks like. So it's three-sided Berkovich tip. It's kind of hard to see, but this is how it looks like. Okay. And this tip here has that are very sharp, so they cleave the diamond in 3 planes, and they get a tip diameter of 20 nanometers. A tip radius of 20 nanometers. You can go on Heisetron.com. This is the company that makes these tips and the nano indenture. If you go on their website, you will find a lot of nice pictures and other things. So then we started looking at the surface topography. So you can scan the surface either with this Berkovich tip or with the atomic force microscope. Okay. Then let's see, again, this screen is so small and this is very hard to see. So what you see here, this RMS value, this is the root mean square surface roughness, that is 3.68 nanometers. See, so our goal was to get anything between 10 and around 10 nanometers. We were actually getting much less than that. And then we scanned it in different, so we scanned between these 2 points, and this point at different places to try to see if we get uniform root mean square surface roughness of less than 10 nanometers. Now why do we need less than 10 nanometers? Because my tip radius is 20 nanometers. So if I have a surface roughness of 40 nanometers or even 20 nanometers, so when I start indenting, I may be indenting like this instead of like this, because it's too rough. So there are all these values. Now I have only 3 nanometers. So even if I'm indenting on a slope, it's very small slope. And as soon as I start indenting, it will move 2 or 3 nanometers into it and the indenter, and it will smoothen out. But if I have very rough surface, I might start indenting here and then keep indenting, and still I'm on the slope. Okay. it looks like when you scan. So this is the fiber, this is the matrix in between, and this is how a surface plot looks like on the fiber. Then so on the fiber's surface, we scanned across, started from the fiber and went over the interface into the polymer. And we wanted to say that, okay, if I go all the way across, what is the roughness? The roughness in this case comes out to be, this is 7.36. So the previous one I showed you was just the polyester, where we got 3.6. Now we have about 8 nanometers. When I'm going from across the fiber and into the matrix, I'm scanning from the fiber into the matrix. So then I've achieved my goal that I want to stay at 10 nanometers of this. But this you cannot do by mechanical polishing only. You have to resort to combination of mechanical and chemical etching. Then we went to this parabolic tip. So this is also made by electrochemical etching of the wire. So this is the process given here. And what happens is that this is how the tip looks like. It's a parabola. Okay? So it's a parabolic tip. And this is at 5,000 magnification. So, and then we actually can put points here and actually come up with the equation of the parabola if you want. So if you indent with a parabolic tip, this is how the indent looks like. But then you can see there is a little bit of pile up, so the material actually moves up, right, on the side. And it depends. If it is very hard, ceramic type material, then it will not move up. If it is like aluminum or polymers, then you will see this happen. That's again our Berkovich tip. And the Berkovich tip indentations look like this. The parabolic tip indents look like a circle. And these look like these triangles. Then we went through all this analysis using contact stress analysis, and there are standard papers which you can find. Okay, I don't know if I gave the reference here. Yes, there is a reference here, Polymer and Farr. That's the classic paper, you can read that. Most of these equations are from that paper. So then we can do our indentation on this very flat, smooth surface, and we can then start looking at the nano indenter-based basic properties like the elastic modulus. Okay, for this is we're using a parabolic tip. This is using a Berkovich tip. Okay. So what we see is that we got with the parabolic tip on the glass fiber, we get somewhere around 80 okay, for this level of indentation. If we go to higher nodes and bigger indents, then we started getting up here about 120, so which is obviously not right. Then if you start getting 120, with the Berkovich tip, even for high nodes, we are getting better values, which is about 50, but that's even much lower than, again, 50 is not the elastic modulus of glass. It's about 72, 75, right? So about somewhere there. So this one, so the parabolic tip for low nodes, not very high nodes, is giving us much closer, more accurate elastic modulus value compared to the Berkovich tip, which is giving us only about 50 on the mean. Same thing for polyester. We were again seeing similar things. And then we also did some on quartz. Now on quartz, which is very hard material, and we are using tungsten, which is hard but not as hard as the diamond. So when we indent on quartz using this parabolic tip, then we are getting too much scatter. Here we are getting much more uniform values with the very hard. So the diamond is even harder than the quartz, but the tungsten is not much harder than the quartz. So the reason at higher nodes, when you try to make bigger indents in a hard material with a tungsten tip, this is what happens. You see all this damage that has happened, so it's no longer a parabolic tip even. It's become flat. So you start getting all sorts of bad numbers for the elastic portions. Okay, now we come to the point where we actually started. What was our goal? We wanted to say that I have a fiber and I have all this matrix around it. If I want to find the properties very close to the fiber, which tip is better? Is it the parabolic tip or the vertical diamond tip? So the answer is here. So this is no fiber coating. So it's a composite still, okay? But we did not use any coatings on it. So what are we using? If I go back, I showed you one picture, this one. So I'm now trying to indent right here. So I start, let's say I start indent with one indent here, one here, one here. So I'm slowly coming close to the fiber. When I get very close to the fiber, what should happen? I should still be getting my values or properties only from the polymer. But that is not going to happen because of this picture, if you see, that I showed you right on the very first one, this one. So, see the stress, the high stress region created will now start containing the fiber also. So, I will see a bias or this bias effect from the fiber, which will mess up my values of the interface region. So that's why we thought that if we go to the so now we find that if I use the vertical tip, and this is the distance from the fiber. So as I keep coming closer and closer, I am getting close to the fiber. Then as I get close, this is 2 microns from the fiber surface. And as I get close to within 1, it begins to shoot up. Okay. So this is the normalized modulus here. So it begins to shoot up. Here with the parabolic tip, I'm almost very close to the fiber, like 0.1 micron. Even then the values don't shoot up. So the parabolic tip doesn't have that much bias effect from the fiber than the other one. Again, if you see here, this is for OTS, the weak bonding created by this ion coating. We see this surge in the values here. We also see, we only saw like a couple of probably bad tests that happened, but by and large they are mostly well contained. They are not shooting up like in the burglars. Same thing again with MPS. Again, they don't shoot up. So this is basically what we were trying to do. And so if you are going to try to use some some way to model the interface into your simulation or whatever you're doing, then this is one way to be able to get some values for the radiation from the bulk to the region very close to the fiber, that interface. I also have some more things here, but let's see. We have a few minutes, so let's quickly look at. These are some references you can look at. We also try to look at implants. Okay. So we have these. So when you have this femur joint here, so people use a lot of ball-type implants. The biggest problem with implants is that when you put that ball inside, it keeps on rubbing. As I move, that ball will move relatively, and what does it do? It has friction, and then some debris will start coming out, so very small chips and all. So after a few months or years, there's so much dust collects inside that ball joint, the artificial joint, that it starts affecting the health of the person. So that was the problem. So we have 6, 7 different types of materials that people were using. That, as I told you on the first day, we also have a hospital, so we have a medical store. So I was working with an orthopedic surgeon, and then he used to give us these samples, and then we would test using the nano indentor what is the friction characteristics and the wear characteristic of the surfaces. So that was the idea here. And so these are the different things that this is cobalt, chrome, molybdenum alloys used. Oxenium is another material that's used. Now oxenium is that it has a softer outside but a harder inside. The other way. It has very hard surface shell, but it is softer on the inside. So, but it is like a metal. So it is heat treated in a way that it becomes hard on the surface and it is much softer inside. And then these are all different types of ceramics. So these are what the balls look like. These are the actual balls that actually go into the femur. And then, so what we did is we used again the Berkovich tip, and we just scratched the surface with different loads. And that's all. We are trying to accomplish here. So you can use different profiles. You can ramp up, scratch, bring it down, or you can keep doing this, okay, and keep doing it for a long time. So this is what a Berkovich tip indentation looks like. So this is what we were doing. For example, then when I embed the tip into it and I scratch it. So this is how the scratch looks like. And this is just a 3D scan. This looks more, appealing, but it's the same thing. What's going on? It's jumping by itself. So then we were able to find. Okay, I think there is some timer or something. So this is the contact stress and the wear volume. So we were able to find for all these different relatively how they are behaving. Okay. So I think there should be at the end. Okay, yeah, this one. So we have the load applied. So this is in micronewtons. See, because we have to apply very small loads in micronewtons because the tip radius and the surface contact area is very small. So even though it seems like a very small load, it creates large stresses. Then this is what we were able to find for the elastic modulus here and the reduced modulus. This is the nanoscale modulus, this is the bulk modulus. So they are fairly close. So we are just trying to make sure that we are not going too far off. Then the wear depth or number of passes. So if I do one pass, then I go back and forth on the same place. Then the wear depth. So this is in nanometers, so we're trying to find those. So as you can see, if you do this ZTA, if you do 6 passes, you get 71 nanometer depth for the wear out. On the oxinium, you get 112. On the chrome polyalloy, you get 374. So you can start seeing the differences. And this is the wear volume versus hardness of the surface. Okay. So as you can see that if you're so this is the hardness in gigapascal. So this is 15 gigapascal. And then this is higher than that. So we saw that the wear volume above 15 gigapascal doesn't vary too much. Okay. So you must have at least 15 gigapascal for the hardness. So and then from all of these we found that oxinium has the least elastic modulus. Oxinium has wear resistance comparable to that of ceramics. And so there were a few things that we were able to come up with and provide them with that some feedback. Okay. And alumina has the highest modulus, hardness, and wear resistance. But there are other problems which I'm not talking about here, and that's the fracture toughness. Okay. So this is just the wear resistance, but it might still break inside. So that's where the fracture toughness comes. So we thought that oxinium is the best material anyway, but that's based on the wear volume over multiple passes. What is the elastic modulus of that material? And I mentioned to you earlier on that the elastic modulus of some of these things, when you do bone implant especially, going into the bone, it should try to match the elastic modulus of the bone. So if it is too high, the oxinium is good only because it has a softer core and a hard surface. There are others, alumina and all are hard throughout the body. So that tends to absorb shocks very well. The oxinium. And its wear resistance is comparable to that of ceramic. So it gives you the best of two worlds. So it gives you ductility from the core and gives you hardness and wear resistance from the surface.
So what is the chemical composition for this oxinium? Chemical composition?
It is, I think it is in here somewhere, I don't remember now, but it should be, let's see if it is in here or not. Maybe not. Okay. I don't recall what it is. It's not here, but if you look at that paper, you will find it in it. But I'll have to look it up. I don't remember it right now. I can give it to you. I thought there is a slide somewhere which has the composition of all of this.
Zirconium. Yes.
Sorry?
Zirconium.
No.
180. Yes, that zirconia is used for making these.
Yes.
Heads.
See, this is zirconia. Okay, I don't have, it seems I don't have the compositions.
Zirconia.
Yes, they are all made anyway. These are actually given by some suppliers who manufacture these, and they are fairly expensive. Each ball, I think, this one ball costs over $1,000 per ball. So they are fairly expensive. Why? Because they don't make too many of those. So the volume of production is very low, but it is very used very for specialized health application. So that's why it's more expensive. Okay, then we can stop here.